I thought I heard another.
Just 2 ways of solving it?
Okay, so 2 different ways. So you have more than one way of doing it? Yeah.
So you have like a structural understanding of what you're doing instead of just...
Like blindly just doing it? Yeah. Those are all valid points, but there's a more important point. Imagine you come in here on day 1 or 2 of class, and I give you this right here, and then I ask you to take the derivative. What are you going to say? What's a derivative? Right? You don't know what a derivative is. See, this is one of these times in math. So the reason I didn't show it to you before is because you didn't have the tools to use it yet, right? This is one of those really awesome times in math, and this happens a lot in math. You know, we started with this idea of the limit, right? And I'm saying as far as human thought and human development here. Isaac Newton came up with this idea of the limit, right? From the limit was born the idea of the derivative, which has to do with slopes of tangent lines, right, on curves, right? And then L'Hopital, this other mathematician, went and proved that, you know what, this derivative idea, I can actually use that idea to come back here and do limits. So it's like you use that to build this, and then you say, oh, well, I can go actually use that to go back and build that. It's almost like you built a machine that actually makes your other machine that built it more efficient. It's weird, right? But it happens a lot in math where you have something down the road that says, oh, wait, hold on, we can actually use this tool to go back and do this. And it's easier to do now, all right? Which is why mathematicians continue to study, you know, because you never know when you're going to come across something that is going to help you solve a problem in a completely different area. You just never know when that's going to happen. So, okay. Let's put L'Hopital's rule up on the board formally. It's in the notes, but just so I'm presenting it to you, I've just verbally told you what it is. Okay, first thing. Wait a minute, where is it? Here we go. Here's the rule. Suppose f and g are both differentiable. So we have f over g, right, these 2 functions, and we took the derivatives of each of them. Well, in order to use L'Hopital, you have to be able to find the derivatives. In other words, the derivatives have to exist. So as long as the derivatives exist, it says that suppose you're taking a limit, and we don't really care what the limit's going to, just that when you take it, you get 0 over 0, okay? If you get 0 over 0, then what you can do is whatever that limit is, whatever the answer is equal to the same limit with the derivatives taken on the top and bottom. That's pretty much what we just did, right? So if you have 0 over 0 in a limit, you can use it. Also, if you ever get positive or negative infinity over positive or negative infinity when you do a limit, then you can use L'Hopital's rule again. So those are the things I've shown you already, right? If we got 0 over 0, we did L'Hopital. We had one where we had infinity over infinity, we use L'Hopital, right? Those are the only 2 times. You cannot use it for any other, there's no other limit that you can use it for. You have to have 0 over 0. You have to have infinity over infinity, or it can be plus or minus, doesn't matter. That's the only time L'Hopital can be used, all right? Which is good news and bad news. It's good news because we have a new tool, right? But what about this table? Remember this? We had all these different forms, right? And so these 2 we can now use L'Hopital on, but all of these, L'Hopital doesn't apply, right? L'Hopital has to have one of these 2, which seems like that sucks, right? It's like a tool you can only break it out every once in a while, right? Seems that way? But there's a workaround, okay? So I'm going to give you a problem now, and it's going to be awesome. Let's just do it right here. Let's do the limit as x goes to, let's go to, what do I want to go to? 0, yeah, let's go to 0, and let's do x natural log x. There we go. Let's do that one. If you look in your notes, we probably did this problem a long time ago. Well, you know what? I need to come into x. I need to come into 0 from the right because I can't put negative numbers in logs. So I have to have that to be a positive number. Right? So if you go look in your notes, I think we did this problem before. All right? So let's talk about what's happening here. If x goes to 0, where does this go? 0, right? Okay. Now times, okay, now the natural log function. We just talked about logarithmic functions last class. Look at the natural log function. What happens is you approach 0 from the right. Last class we talked about natural log. We said it looks like this. Right? How do you know that? Because you took college algebra, and last class I told you that's what natural log looked like, and I told you it would be important to know that. So this is it right here, right? This is what the natural log function looks like. So as you approach 0 from the right, where is it going? Negative infinity. That is an indeterminate form. Something's getting small, and something's getting really big and negative, right? So there's like this tug of war happening. This is an indeterminate form, right? It's one of the forms off that table I just showed you. Can we use L'Hopital's rule? No, it's not 0 over 0. It's not infinity over infinity, is it? Right? So we can't use L'Hopital. So what do we do? Well, there's a standard approach, okay? Here it is. Okay? This is the standard approach. You are going, whenever you see this, 0 times infinity or infinity times 0, positive or negative, doesn't matter. If you ever see this form and you want to use L'Hopital's rule, what you have to do is this. You have to choose one of these two. You get to choose. You have freedom here. You choose one of these and you drop it to the denominator. What? Okay, let me do it and then see if it makes sense. I am going to rewrite this limit. I'm not using L'Hopital yet. I am going to decide just for this first time through, I'm going to leave the natural log of x where it is, but I'm going to drop the x to the bottom. Now, when I say I drop the x, here's what I actually mean. I'm going to rewrite an x on the top instead as a 1 over x in the denominator. Do you all agree that that's just me rewriting the problem in a different way, but it's the exact same problem, right? Because 1 over x on the bottom, that x would actually flip up and go next to the natural log, and you'd be here, right? So I picked that x and I pushed it to the bottom as a 1 over x. Understand that or not? That's just algebra, yes? Yeah? Okay, now why did I do that? Let's run through the limit again. Okay, run through the limit. Where does this go as x goes to 0? Well, we already said that, right? Where does it go? That goes to negative infinity. Okay, now the bottom, the whole thing, what happens as x goes to 0? 1 over 0. What happens there? If you have 1 on top and on the bottom you have a number that gets really small, what happens to that ratio? Take the number 1 and divide it by a tiny number and you get a big number or small number? I'm not hearing what you're saying, sorry.
Infinity.
Infinity, yeah. It would become infinitely big. So again, we're going back to our knowledge about limits from the past. If you have a fixed number on top and your bottom gets small, that ratio gets big. If you take a fixed number on top and divide it by a very small number, that will be a very big number, right? So do you agree that the 1 over x, as x gets really, really small, that ratio becomes infinitely big? And now you have a negative infinity over positive infinity. Y'all see that?
Why is it negative infinity?
Where? The natural log function, you're approaching 0 from the right. There's the picture of natural log. You're approaching 0. Here's 0. You're approaching on the graph. You're approaching the 0 from the right-hand side, and the graph is headed where? Negative infinity, right? That's why the top is negative infinity. And then the bottom's positive infinity. We're okay with that? See, this form right here, 0 times infinity, I can't use L'Hopital. I can only use L'Hopital on 0 over 0 or infinity over infinity. And the signs don't matter. It doesn't matter if it's positive or negative. Just forget those. Just see infinity on top and bottom, you can do L'Hopital. If you see zeros on top and bottom, you can do L'Hopital. But you can't do it here. So I forced it to look like this. I did that myself. I picked one, I dropped it, and then I got what I needed. Now I can use L'Hopital. All right? Yes?
This might be a silly question, but what if you had like something where you have infinity and 0?
Infinity where? On top and 0 on the bottom?
I guess.
Okay.
Like you still wouldn't be able to.
Do you want me to do that right now, or do you want me to wait and I can answer that after? It's up to you. Okay, so remind me. When I finish this problem, I'll give you an example of that and how do we deal with it. Okay, so look. I'm going to use L'Hopital at this point, right? L'Hopital says I take derivative of the top and bottom separately, right? What is the derivative of the top? We just learned that last class. 1 over x. That's it. That's the derivative of natural log of x, 1 over x, from last class. Over, okay, and this is the part most people screw up. What is the derivative of 1 over x? People will tell me 1. No. You have to look at 1 over x. You're trying to take the derivative, right? You have to look at that as x to the negative 1, right? That's what that really means, right? You're not just, we do not take the derivative of a quotient by doing just derivative top and bottom, right? I mean, don't regress here. You got to still follow the same rules we've had. What's the derivative of this? Negative 1 x to the negative 2, right? You bring the power out, you subtract 1 from the power. But that's really negative 1 over x squared. All I did there was drop the x to the negative 2 down to the bottom. Y'all agree? So the bottom is negative 1 over x squared. Now don't go running your limit again yet. Let's see if this cleans up algebraically. I have a fraction over a fraction. Can't I flip this one up and multiply? Right? I can flip that up and multiply. So I'm going to continue that over here. This becomes the limit as x approaches 0 from the right. I'll have the 1 over x, and then I brought the other one up and I flipped it, so x squared on top, negative 1 on the bottom. And then can I cancel an x there? Right? I can cancel 1x from both of those. So I get limit x approaches 0 from the right. When I cancel one of the x's, I get an x on top and I get a negative 1 on the bottom. And now that you've done that cleaning up, let x go to 0. What do you get if x goes to 0 here? 0 over negative 1 fixed, so you don't get bad anymore, right? 0 over any non-zero number is just 0. So your answer is 0. Yep.
You only put, like how you put your L circle, you only put that once?
You only use the L'Hopital symbol when you actually do the step of taking the derivative of the top and bottom. Yeah? Okay. If we ever see 0 times infinity, we pick one and drop it, right? I picked x and dropped it. I could have picked the natural log and dropped that instead. I'd like to show you that because I think you'll agree when we do it that way that it's not going to work out very nice. And that even though you can choose, there's usually a better choice of what to drop and what to leave up top. So let's redo this problem. This time, I'm not writing the L yet. This is just me dropping. I'm going to leave the x on top And when the natural log drops to the bottom, it becomes 1 over natural log x. Okay, that's what it becomes. Right? I mean, that's the same thing, yes? Now check, let's see that we can use L'Hopital. Let x go to 0. Where's the top go? 0. Okay, over. Okay, be careful here. Look at this right here. Where does that go? Just the bottom there. Where, if x goes to 0, where does the natural log go? That piece right there goes to where?
Negative.
Negative infinity, right? What's 1 divided by a huge number? Ooh. 1 divided by a huge number. You're thinking huge number divided by 1. What's 1 divided by 10? What's 1 divided by 100? What's 1 divided by 1,000? What's 1 divided by 1,000,000? What's 1 divided by 1,000,000,000,000? What's happening to that? It's getting smaller, right? So 1 divided by negative infinity goes to 0, which means this whole bottom piece is headed to 0. Can you use L'Hopital then? Yeah, 0 over 0, right? So I can use L'Hopital. Now what's good about L'Hopital here is that the derivative of the top is nice, isn't it? Derivative of top is 1. What sucks about L'Hopital's rule here is the derivative of the bottom. Because, again, you cannot do the derivative of these, you can't just take derivative of the bottom. You have to treat this as a quotient rule, which means over here I'd have to do this. The derivative of 1 over natural log x. I can't even do this. I mean, I could, but it's probably better just to do the good old-fashioned quotient rule here. What's the derivative? How do we do a quotient? Derivative of the top times the bottom minus derivative of the bottom times the top over the bottom squared, right? So what's the derivative of the top? 0 times the bottom. That's not going to matter. Minus what's derivative of the bottom? 1 over x times the top. 1 all over the bottom squared. Not a very pretty derivative, is it? Gone. Negative 1 over x is what we have on top. On the bottom, natural log of x squared. That's your derivative. And now I need to put that over here. Compare that to what we just did on the, right? On this one, I dropped the natural log down and things got really ugly. When I dropped the x down, when we did it previously, things got really nice, didn't they? So you want to, the more you can foresee what's going to happen, depending on which one you drop, the more you can foresee what those derivatives are going to look like, the easier it's going to be for you to make the choice of which one to do. But if you can't foresee it, you're just going to have to just try each way and hope that you pick the right way first. Yes?
So is it usually going to be easier to drop, like whatever doesn't have a log?
Yeah, it's usually, you drop, usually, not always, you drop the thing that's doesn't have like an exponential or a log or some sign or something like that. But not always. Okay, so if we see 0 times infinity, we pick one and we drop it, right? And then we do L'Hopital. Let's look at another indeterminate form. How about this one? X to the x. Limit x goes to 0 of x to the x. So what form do we get here? If I let the base go to 0 and the exponent go to 0, I get 0 raised to the 0. That is an indeterminate form. It's indeterminate because the base is getting really small, right? But anything raised to the 0 should be what? 1, right? So there's like this contradictory things happening here. The base wants to become 0. the exponent wants to turn the whole answer into 1. So this was indeterminate. Not everything is indeterminate. I mean, some expressions are not. Oh, I never got to your example. I can do that before I do this. So these are the indeterminate forms. I'm looking at 0 to the 0 right now. So the question was, what if you had like infinity over 0, something like that? So let me just, separate problem than that. If I said, what's the limit, let's do this. X goes to 0 from the right of natural log x over x. There we go. So where's the top headed? Where's the natural log headed as you approach 0 from the right? Negative infinity, right? That's the one we just did a minute ago. So that's negative infinity over, where's the bottom headed? 0. This is what you're asking, right? Okay. So this is not 0 over 0, right? It's not 0 over 0. It's not infinity over 0. So there's no L'Hopital here, but is this an indeterminate form? Is this something where we don't know what the answer is? Well, we actually do know this answer. We don't have to do any more work. Just think about what's happening. Your numerator is getting really big, right? And negative. So let me just give you some big negative numerators. 1, here, let me make it bigger. Negative 100. Let me give you a bigger one. Negative 1,000,000, right? And then, I don't know, I could keep going, right? Negative 1. That's bigger, right? We're taking those and we're dividing them by numbers that are getting what? Numbers that are getting smaller, right? Headed to 0. So maybe this is 0.1. This is 0.00, or 0.01, 0.00001, 0.000000001. What happens here? What's going on? This number on top's getting bigger, and the number on the bottom is getting smaller. So that ratio, as I go out, the ratio is getting what? Bigger, right? It's getting huge. What would happen if you took that huge number and divided it by the tiny number? You would get a bigger number, wouldn't you? So it's almost like they help each other out. It's almost like they're helping each other. It's like the numerator is like, I'm going to get big. The denominator is like, hey, well, I'm going to start dividing you by small, small numbers, which is going to help us get even bigger. Make sense? So the answer to this would be negative infinity, and there's no work to be done. Maybe it would be easier if you flip it over. What if I gave you this limit? Look at it that way instead. On this one, you get 0 on top and you get negative infinity on the bottom, right? So the top's trying to get small and the denominator's trying to get big, right? So the top number's like, I'm just a little tiny number, and then the denominator's like, well, I'm going to divide you by a big number, which is going to cut you into smaller pieces, which can make you even smaller, right? So they help each other, and this would head to where? 0. Does that make sense or not? Yeah, you sure? Now, if we get 0 over 0, that's a problem. We don't know who wins. If we have infinity over infinity, we don't know who wins. But in those two cases, they're actually assisting each other in getting to the answer. All right, now this one, let's get back to this. We are not allowed to use L'Hopital, right? No L'Hopital here, because we can only use L'Hopital if we have 0 over 0 or infinity over infinity. So how are we going to do this? Well, there's good news and there's bad news. The good news is that we are going to be able to use L'Hopital. The bad news is that we are still going to have to do a step that we did when we did this problem back in the beginning of the semester. I told y'all, whenever you see one of these forms where it's like an exponent, what you first do is you call this limit y. Okay? You call the limit y. And we do that so that the next step we can bring the natural log in on both sides of the equation. So I'm going to take the natural log of the left side. And on the right side, again, if you go back and look at your notes and review the lecture videos, you leave the limit and you bring the natural log in after the limit. So you do the natural log on this side, and then on this side you put the natural log here. And do y'all remember at all why I brought the natural log in? Yeah, it allows me to take this x right here and drop it in front. That's why we bring the natural log in. So my next line looks like this. Natural log y, I'm writing the left side, equals the limit as x goes to 0 from the right. I drop the x out in front times natural log y. Questions on that? You're good? Okay, now look at that limit you have on the right-hand side. X goes to 0 from the right. Where does this go? 0, right? Where does that go? Negative infinity. Wait a minute. That's the same problem we just did before this one, isn't it? That's the exact same problem that we just did. Right? The right-hand side is exactly the problem we just did. So what I would do is, well, you tell me, what do I do? Take one of them and drop them, right? So I'm going to actually write the steps here so you can see how this would be written. Natural log y equals limit. X goes to 0 from the right. I'm going to leave the natural log x on top. I'm going to drop the 1 over x below it. Now I know that I have negative infinity over infinity, because we talked about this a few minutes ago. And now I can use L'Hopital, right? So watch how I do the L'Hopital. I do natural log y equals, I'm using L'Hopital now, limit x goes to 0 from the right. Okay, when we did L'Hopital, we got 1 over x on top, and on the bottom we got negative 1 over x squared. I'm not showing that work because we just did it a second ago. What did this answer turn out to be? I think I've shown enough of the work. What did this answer turn out to be on the right-hand side? What did we get? X over negative 1. And then we took the limit and we got what answer? 0, right? So this side is 0, right? That's not our answer. What's our left side say? Natural log of y equals this right here becomes 0. We are not interested in what natural log of y is. We're interested in what y is, right? We want to know what this limit was to begin with. We called it y, didn't we? Then we brought the natural log in so we could drop the x out. We dropped the x out so that we could then pull one and drop it down so we could use L'Hopital. We used L'Hopital, we got an answer. But that's what natural log of y is. So how do I recover the y back from this? I have to kill off the natural log. How do you kill off natural log? The exponential function. So I'm going to do e on both sides right now. I do e raised to the natural log y equals e raised to the 0. And if I do that, e to the natural log gives me y, and then e to the 0 is 1. Anything to the 0 is 1. So what is the answer here? 1. Okay, I think you've had enough for the day. Your homework is to make sure that you have done all the homework. I would expect at this point that you have done the 3.3 as much as you can in 3.3 derivatives of exponential logs. The 3.5, those problems due for homework, that's the inverse trig functions that we started class with, right? The 16 through 27. And then as far as L'Hopital, we're just, I mean, we still have more to do with L'Hopital. You could start L'Hopital, you could, I don't have my book with me. You could probably look at the first maybe 10 problems or so in L'Hopital. I wouldn't go past 10 because they get more complicated. All right, next class we'll do more L'Hopital. More L'Hopital next time, and then the definition. I'll put it up here. Just remember, all these notes are online, right? I just don't want y'all to forget that. Everything I put up here on the board is also see. There's two of them, so there's two different pieces, so that's the best I'm going to be able to do right there. There we go. It's those two. I will.